Hey, welcome back to Introductory Statistics. In this week, we're going to talk about chance errors in sampling. We'll cover chapters 20 and 21. We're going to discuss sample surveys, and surveys tend to involve chance error, and we'll talk about how to find the likely size of this chance error. And especially we'll look at simple random samples from a population where we know some information about, and it turns out that we can see that this chance error actually depends on the size of the sample but not the actual size of the population, which is interesting. So suppose I have a study that look at some representative cross-section of Americans, and say that we have 6,672 Americans who were picked for this survey, and of those about 3,091 are men, 3,581 are women. And now suppose that we want to interview these people and ask some questions and see if we can try to understand the some statistics for these people. And suppose we don't have the resources, we're going to only sample randomly 100 of these Americans, and we expect that with the simple random sample, the expected value for the sample percentage should equal the population percentage. So for example, since 46% of the population in this example are men, then we expect that when we pick our 100 random sample, our sample should reflect that, and so we expect that even in our sample that we have 46% of the sample will be men as well. However, of course, the sample percentage will not exactly equal to the expected value. There could be some chance error. Every time we do a different random sample, that number can change. So we'd like to know, how big is this chance error? And so this answer is given by the standard error. And so I think we talked about this a little bit in the last lecture, but so for this problem, it turns out that the standard error is 5 percentage points. In other words, we expect that the percentage of men in the sample to be off the percentage in the population by about 5 percentage points or so. So we're going to discuss how this number is calculated. So the idea here is that we're going to first find the SE, the standard error, from chapter 17 for the number of men in the samples, and then we're going to convert that into percentage. So really this section, the math is very similar to the last lecture in chapter 17, where we discuss the standard error. The only thing is that we got to convert that into a percentage, and so that means that we have to divide that by the sample size and then multiply by 100 to convert it to a percentage. So for example, in this case, let's try to find out what the standard error is. And so we remember from the last chapter that we can look at the box model and try to convert this into a box where we have a bunch of tickets, and where a ticket is a 1, it represents a man, and a ticket is a 0, it represents a woman. And if I pick out 100 tickets from this box consisting of the 6,000 or so people, then here's the box model. We have 3,091 of them are 1s, 3,581 are 0, which represent the woman. And so we're going to do this without replacement. And so that's essentially the box model. And so that means that if I take out 100 tickets from this box, we're going to calculate now the SE for such a random sample, and so the way we need to find the SD of the box. And remember, there was a shortcut that we talked about, where if it's a box of 1 to 0, it's just 1 minus 0 times the square root of fractions of 1, fraction times fraction of 0. So doing that will give us the SD of the box to be 0.5. And so by the formula we got from chapter 17 was the SE would be the square root of 100 times the SD, so that would give us 5. The standard error for this sample is 5. That means that if I pick 100 draws from this box, then we expect to get about 46 men, give or take 5 or so. So that 5 is the standard error that we computed in the previous lecture. And so to convert this number 5 into a standard error in percentage, all we have to do is convert it into a percentage. So we take 5 and we divide it by the sample size. So 5 divided by 100 is 0.05, and that's, as a percentage, is 5%. So that means that when I sample 100 people, I expect that the percentage of men is about 46%, and then the standard error percentage is 5%. So really it's the same problem as chapter 17, except now that we have to convert everything into percentages. So here's the formula. The formula for SE for percentage is the same formula for SE for number from chapter 17, and then just convert it by dividing by the size of the sample, multiply by 100% to convert that number into a percentage. So again, really it's the same answer as from before. It's just a simple conversion to a percentage. Now what happened if we take the sample to be bigger? What if we took 400 instead of 100? Then with 400 the SE would be 10, so notice the SE went up. However, 10 as a percentage of 400 is only 2.5%. So the SE for percentage, right, taking 10 divided by 400 is 2.5%. So this shows that multiplying the size of the sample by 4, if I increase my sample size, it actually cut my my SE for percentage by 2, which is by the square root of 4. So for example, the SE for, if my sample size was 100, the SE for was 5, the SE for percentage is 5%. But when I increase my sample size to 400, the SE went up to 10, but the SE for percentage though went down to 2.5%. And so, I mean, this is not surprising, because if I increase my sample size, then I should be getting my error to go down, because as my sample gets bigger, it should represent better my population. So this says that multiplying the size of the sample by some factor divides the SE for percentage not by that whole factor, but by its square root. So in this case, for example, by increasing the sample size by 4, we were able to reduce the SE for percentage by square root of 4, which is 2. So this says that increasing the sample size of a poll by some factor decreases the standard error for percentage for the poll, not by the whole factor, but by its square root. And so this is important as we think about things like the cost of polling. You know, we can't just keep increasing the size of our sample size, because there's this return where the percentage of the error decreases only by a smaller factor, not by the whole factor. So we saw in the last example, increasing the sample size by 4 from 100 to 400 helps decrease the size of the error by a factor of 2, not of 4. So the formula is actually exact if you do it with replacement, but when we do it without replacement, which is what we do when we poll, it's pretty close. So so this is a good approximation. Okay, so now we're going to talk about how the SE for percentage can be obtained from the SE for the corresponding number. But these two numbers actually behave differently. So, and we saw this earlier, when the sample size goes up, the SE for the number goes up as well, but the SE for the percentage goes down, and that's because the SE for the number goes up slowly relative to the sample size. So, of course, as I increase my sample size, my standard error will go up, but it goes up relatively slow compared to the sample size. So now we're going to talk about how to use this SE for percentage, and then how to use normal curve to compute probabilities. So suppose that in a certain town we have a telephone company that has about 100,000 subscribers, and we're going to pick out 400 of them as part of some research study. According to data, let's say that we know that 20% of the company's subscribers earn over $50,000 a year. So the question we want to know is the percentage of person in the sample with incomes over $50,000 a year would be around blank, give or take blank or so. So notice this problem is interesting because it's kind of backward, because we do have access to the information about the entire population of the subscribers, and we know that 20% of the subscribers earn at least $50,000 a year. And so it seems kind of silly that we're doing a random sample, and we're trying to learn something that we already know, which is what percentage of the sample is earn that much money. But so later in the next lecture, in fact later this lecture, we'll flip this problem around and make it more useful. But right now, we just want to use this problem as a way to see how our data will reflect our population, assuming that we know something about the population. So first step is to make a box model. So again, this box contains the entire 100,000 people, and because we know 20% of them earn at least 50K, we know that 20,000 tickets would be ones, and then 80,000 would be zero. And now we're going to pick 400 tickets from this box. Okay, and then we can find the expected sum. Because 20% of 400 is 80, we expect that we get 80 tickets to be ones. And then using the SD shortcut, the SD for the box is 1 minus 0 times square root of 0.2 times 0.8, which is 0.4. So the SE for number is root of 400 times 0.4, which is 8. So this is all from chapter 17. So that means that the sum of the numbers of ones is about 80, give or take 8 or so. If I pick out 400 tickets, I expect to get about 80 ones, meaning 80 people in the 400 that earns at least 50K, and then the error is about 8 or so. Now, because we're thinking about percentages, we have to convert those numbers into percentages. So 80 out of 400 is 20%, 8 out of 400 is 2%. So that means that we expect to get about the sample percentage. We expect to get a 20% sample percentage, and the error for that percentage is 2%. And the 20% is not surprising because 20% reflect the 20% of the population. So we're not too surprised because the population of the people who earn 50K or more is 20%. So when we draw 400 tickets, it's not surprising that our expected value for the sample percentage is also 20%. But in this case, because we pick out 400 people, our error is about 2%. So it's possible that in our sample we don't get exactly 20%. There's a chance error, and in this case we compute that the error is 20%. No, sorry, 2%. So the percentage of high earners in the sample would be around 20%, give or take 2% or so. So now we want to do another example, which is the continuation of the previous example. We want to find the chance that between 18% and 22% of the person in the sample earn more than 50,000 a year. So now we want to convert all this into a chapter 5 problem, which is a normal distribution problem. And so because the expected value is 20% and the SE for percentage is 2%, we convert all that into standard units, which is z-score from chapter 5. So 20% correspond to, because that's the expected value, correspond to 0. And then 18%, if you convert it into a z-score, 18 minus 20 divided by 2% gives you the z-score of -1. 22% gives you SD of a z-score of plus 1. Again, that's because the error is 2%. If I'm at 80%, I am 1 error to the left, which is -1. And then if I'm at 22%, I am 1 error to the right of the expected value, which is +1. And then from the z table, we can find out that the area between -1 and +1 is about 68%. That's from the z table. And so this says that the chance that our person income is well, this says that the chance that between 18% and 22% of the person in the sample earn more than 50,000 K or so. Okay, now we're going to take this problem and flip it in chapter 21. And this is kind of the reverse. And with this reverse problem is much more useful and more common in practice. And so in the previous chapter, chapter 20, which we just discussed, we reason from the box to the draw. So if we know something about the box, the population, we can say something about the sample, what to expect when we pick a sample. And then so draw were made at random from a box whose composition is known, and then But now, in practice, this doesn't happen. Usually, we don't know anything about the population. That's why we want to do a poll or a study or a survey. And so it's more useful to turn this reasoning around, going from the draws, the sample, to the box. So this is called an inference, where we pick a sample, we learn something about the sample, and then we infer some information about the population. So that is, given a population, we like to understand some parameter. We sample, we do a survey of some sort of a small group of people, and then estimate the parameter of the population from the statistics of the sample. So again, we want to understand the parameter of a population. We do a poll of a small group of people, and the statistic from the sample, which we can compute, we can say something about the parameter of the population. So inference is basically what we're going to talk about in this chapter. So suppose that a survey organization wants to know the percentage of Democrats in a certain district. We might estimate that by using a simple random sample. And so we're going to use the percentage of the Democrats from the sample to say something about the percentage of Democrats in the entire district. So we're going from the draws to the box, the sample to the population. Okay, and so this is the idea of just polling, taking surveys and trying to learn about some population parameter. So suppose, let's do an example where you have a candidate who wants to enter a primary a race in the district, and let's say there's 100,000 voters, but this candidate wants to know whether he has a good chance of winning, whether he should even enter into the race. So he hires a survey organization which takes a simple random sample of 2,500 voters, and in the sample, the organization found out that 13.28 of the people favor the candidate, so the percentage is 53%. So the candidate is hopeful that 53% is above 50%, so he's hopeful that, according to this, he has a good chance of winning, and so he should enter the race. But one question is that, well, what do we know about the size of the chance error? I mean, this is one survey, so what if we do the survey again? What if it's less than 50%? And so we want to know is according to this survey, what is the chance error? What is the error, so that we know how to understand this 53%? Because if the error is big, then we won't be so confident about this number. But if the error is small, if the chance error is small, then we can be more confident that this 53% is good enough for us to enter the race. So we're going to do a box model again. 100,000 is the population, so we're going to do box of 1s and 0. And so 1s are the people who will vote for him, 0s are the people who will not vote for him. But the problem is that this box, we don't know anything about this box, because we're trying to understand something about the people, how people vote. So we don't have the information, unlike the previous chapter where we have the information, like the Comcast example, telephone example earlier, actually. But in this example, we don't know the composition of the population. So we're making 2,500 draws from this. And so the problem is that in the formula for the SE, we need the SD of the box. The problem is that we don't know anything about this box, so we can't compute the SD of the box by taking that shortcut formula that we talked about. So this is a problem. We seem to be kind of stuck because we don't know anything about this population, and so the way we're going to do this is we're going to kind of use this trick where we're going to take the sample that we just draw, the 2,500 sample, and use information about the sample, and then kind of use that to estimate the population of the box. So this seems kind of circular reasoning, right? Because we try to find out something about this box, and then we take some sample, but we need information about this box, so we use the sample that we found to estimate the information that we want to find out about the box. It seems kind of circular because isn't our sample supposed to be helping us understand the population, and so it seems kind of a circular reasoning a little bit, but it turns out to work okay in practice. And so the way we're going to do that is that we're going to use the sample information to estimate the population parameter. And so we do that by taking 1328 divided by 2,500. We get 0.53, and then that means the other 0.47 do not support him. So we're going to use that to find the SD of the box. Remember, to find the SD of the box, we need the information about the box, but we're going to, for now, this is called the Bootstrap method, where we use the information about from the sample and then to calculate the SD of the box. So now we can compute the SD of the box by using the information from the sample and find out the SD of the box is 0.5. That means the SE, the SE number is root of 2500 times 0.5, which is 25. And then convert that into a SE for percentage by dividing by 2500, we get 1% SE error. So that means that the candidate expects to get about 53% of the vote, and the standard error for percentage is about 1%. So, and because 53% is actually 3 SE away from 50%, he's on the safe side. That means that the error is small enough that he should be confident that he should get at least the 50% of the support, and that he should enter into that race. So this is called the Bootstrap method. Again, this method says that when sampling from a 0-1 box whose composition is unknown, we're going to use the SD. The SD of the box can be estimated by substituting the fractions of zeros and ones from the sample for the unknown fractions in the box. This estimate is actually pretty good when the sample is large. Okay, so here's another example. Say that some university had about 25,000 students. We want to estimate the percent of people who live at home. So we do a simple random sample of 400 students, and we've surveyed them. And it turns out that of those who were surveyed, 317 of them live at home. And we want to use this information to estimate the percentage of students at the university who are living at home. So this is kind of a standard problem in polling, right? Because we want to know something about the general population. We do a sample, and we use that sample to infer something about the general population. So this is a good example of a typical polling problem, and now we want to understand that how to measure the error of our poll. And this is what we see when you watch TV. They say something like, here's the a certain candidate, and the survey says based on polling that they're expected to get about 50 a certain percentage of the vote, but then there's an error attached to it. So essentially now we are trying to figure out, we're learning how to compute this error when we do a poll like that. So here's the sample percentage. 317 divided by 400 convert into a percentage is 79%. So we're going to estimate the population percentage to be 79%. That means we expect that 79% of the students are from the university also live at home. But how do we compute the standard error for this poll? Well, we need the box model again. Again, 25,000 tickets is the whole population of the student body, but we don't know that information. We don't know how many of them live at home. So we look at the 400 draws. Again, because we need the SD box of the population, we couldn't do this before, so the Bootstrap method said that we're going to use the SD of the box. So based on the box, we know that 0.79 of them are at home, 0.21 is doesn't live at home. So from that, we're going to use the SD. We're going to estimate the SD of the box by the Bootstrap method by computing this SD using the sample parameter, the sample information of 79% at home, and we get that the SD of the box is 0.41, and then based on that, the SD for the number is root of 400 times 0.41, which is about 8. So this says that the error, the chance error, is about 8. That means that the 317 people who live at home, that error is 8. Now we have to convert these into percentages, and so 8 out of 400 is 2%. So this says that the SE for the sample percentage is 2%. So that means that we expect that the university student body, 79% of them live at home, and the error is about 2 percentage points. So essentially, this is how surveys are done and how we can compute those survey errors. Let's talk about confidence interval. So 79% of the students in the sample will live at home. That's from our sample percentage. And the question is, how far can the population percentage be from 79%? That was our estimate, but we want to know how far can this population percentage be. the standard error was estimated to be 2%. So that means that we want to use this 2% to kind of find a bound for the population percentage. So the way we do it, we're going to take 79%, which is the midpoint, and we're going to add and subtract 2 standard errors from 79%. So 2 standard error using 2% is 4%. So that means that my interval that I'm looking at here should be from 75% to 83%. So this is called the confidence interval for the population percentage, with a confidence of about 95%. So that means that we are 95% confident that the population percentage is caught between this interval from 75% to 83%. So again, we use the sample percentage, and then we find that we use the SE percentage, add and subtract 2 SE, left and right of the sample percentage, and that interval is the 95% confidence interval that tells us how confident we are to catch the actual population. Remember, this sample population percentage is an approximation, so we want to know, how do we figure out approximately where the population percentage is based on the sample percentage. So if we add only 1 SE, then we are 68% confident. If it's 2 SE, that's a 95% confidence interval. If it's 3 SE, then that's a 99.7% confidence interval. So of course, the bigger the interval, the more confident we are to catch that population percentage in that interval. So suppose we have a simple random sample of 1,600 person, and you want to estimate the percentage of Democrats from this town, which has 25,000 voters. And so say that from the sample, 917 of them are Democrats. We want to find the 95% confidence interval for the percentage of Democrats among all 25,000 voters. So the sample percentage is 917 divided by 1,600. That's from our sample. So that's about 57.3%. So that's going to be used to estimate the percentage of Democrats in the general population. But we want to know now, let's find out the error and see if we can find that interval. So the standard error, right, again, we need the box model. And so the SD of the box can be estimated by the Bootstrap method. Remember, the Bootstrap method is to use the data from the survey to find the SD of the box. And so that turned out to be 0.5. That means the SE is about 20. So that means that 20 is the size of the error based on the 917 that we found from the sample data. Convert everything to percentages. So 20 out of 1,600 is 1.25%. So this says that the percentage of the population, the percentage of Democrats in the general population is probably around let's see, 57.3%, and that error is about 1.25%. And so to find a 95% confidence interval for the true percentage of Democrats among all voters, we take the sample percentage, 57.3, you add or subtract 2 times the SE percentage, in this case is 1.25, so that means we get the interval between 54.8% and 59.8%. That means that we are 95% confident that the true percentage of Democrats in the general population is between 54.8% and 59.8%. So the confidence interval here depends on the sample. If I take another sample, then I might get a different confidence interval. So we want to understand this confidence interval. So with some sample, the interval here traps the population percentage. With other sample, it does not trap. So for example, the left sample here traps the true population percentage that we're trying to estimate. The one in the middle doesn't. The one on the left doesn't. And so this 95% confidence interval, the way we interpret it is that for about 95% of all of the samples, this interval will contain the population percentage, and the other 5% is not. So that means that if I were to repeat this survey 100 times, 95% of the time, my survey confidence interval does include the true population percentage, and maybe if I'm not lucky, some in my survey might not. So that's how you interpret it. Is that if I were to repeat this survey a certain number of times, then 95% of the time my survey interval do capture the population percentage. Okay, that's basically so this confidence interval is used when estimating an unknown parameter from the sample data, and the interval gives a range for the parameter and a confidence that it covers that range. Okay, thank you.